Welcome to online video training for the CTI Workbench Integrated Development Environment. This is Course 1, Part 5. Programming in Function Block Diagram. Running time, 20 minutes. Let's get started. Function block diagram is a graphical language, widely used in Europe. Its appearance is very similar to an electrical schematic. It consists of blocks containing functions, and lines between blocks, which depict data or signal flow. FBD is ideal for continuous processes. The Workbench FBD editor is a powerful graphical tool that enables you to enter and manage function block diagrams, according to the IEC 61131 standard. The editor supports advanced graphic features such as drag and drop, object resizing, and connection line routing features, enabling you to rapidly and freely arrange the elements of your diagram. You can also insert in an FBD diagram graphic elements of the ladder diagram language, such as contacts and coils. During runtime, FBD is executed top to bottom, and left to right. The higher object always executes first. If two blocks are at the same position vertically, then the leftmost block executes first. In this example, the instructions are executed in the following order: add, multiply, divide. When executing a block, if it gets an input from another block, the feeding block is executed first, so the input will be defined for the second block. In this example, the instructions are executed in the following order: divide, multiply, add. In Workbench, function block diagrams consist of these components: function blocks, variable tags, comment text, interconnection lines, network breaks, labels, jumps, and structured text instructions. We'll create a new program in function block diagram, so we can look at these components in more detail. Function blocks consist of internal code and private variables, with defined inputs and outputs. For standard function blocks, the code is part of Workbench, and you're not able to see it. For user-defined function blocks, you are able to see the code. When looking through the list of objects, you'll notice two different icons used next to the name of the objects. The icons which are filled in are function blocks. The non-filled icons are functions. You may also notice that some objects are bolded. This means they are IEC 61131 standard functions or function blocks. Using the bolded ones, where possible, could make it easier to convert your programs to another IEC 61131 implementation from a different manufacturer. To use a function or function block in your diagram, simply drag it from the list to the desired location. For function blocks, you will notice they come in with question marks at the top. This is the space for the unique variable name of this instance, and needs to be filled in. If you have already defined a variable name for this instance, just drag it from the variable list into the function block. You can also define a new instance by double-clicking on the function block and completing the variable definition dialog. Variable tags can be inserted using the Add Variable icon. Once inserted, you can either drag an existing variable onto the box, or double-click the box to bring up the variable definition dialog. You can resize the variable boxes to show the variable comment tag, if this field is filled in. You can insert comment text anywhere on the diagram. There are two ways of drawing interconnection lines in the editor. We've placed a multiply function on the diagram, and we'll connect the two variable tags we just created. You can use the Add Arc icon, which allows Workbench to automatically route the line between the endpoints. Notice that you must draw the line in the direction of signal flow. You can also use the corner icon to manually route the line. Network breaks can be added to make the diagram easier to understand. The brake line is drawn completely across the width of the diagram, and no other object can overlap the network brake. Once drawn, brake lines can be selected and moved vertically to another location. Brakes can be entered anywhere on the diagram and have no effect on program execution. Network brakes can also be used for browsing the diagram. Press Control Page Up or Control Page Down to move to the next or previous network brake. Labels are used as a destination of a jump instruction in FBD language. A label consists of a unique name, followed by a colon. A label can be inserted anywhere in the diagram, and is not connected to any block. A label can also be used for documentation purposes, such as marking parts of programs to improve its readability, without being used as a target of a jump instruction. A jump to label instruction branches the execution of the program to the point immediately following the specified label. In FBD language, a jump is represented by this symbol, with the label name inside. A variable tag precedes the jump, which must be a valid Boolean signal. The operation is performed only if the input is true. Use caution when putting backward jumps in your program, as it could lead to infinite loops that block the target cycle. Complex structured text expressions can be used with any graphic element in FBD language, making it possible to simplify the diagram when a calculation needs to be entered. The expression must be written in ST language, and must fit the data type required by the diagram. For example, an expression put on a contact must be Boolean. All available functions and function blocks are listed in the object pane, grouped by category within folders. The All category enables you to see the complete list of available blocks. The Recent category contains the last used blocks. The Used category shows all blocks which are used in the program currently open for editing. A Project category lists all UDFBs and subprograms in the project. To insert the block in a program, simply select it in the list, and drag it with the mouse to the desired position in the diagram. Press the F1 key when a block is selected. To get help about its function, inputs and outputs. You can also double-click the mouse on a block to change its type, and set the number of input pins, if the block can be extended. Inputs to function blocks can be negated by highlighting the connection line and pressing the spacebar. To insert a variable, you can simply drag it from the Variables pane to the variable box where you want to attach it. Alternately, you can double-click on a variable box to bring up the variable editing dialog. The diagram is entered in a logical grid, and all objects are snapped to the grid. You can display or hide the grid using the View menu. The XY coordinates of the mouse cursor are displayed in the status bar. This helps in locating errors detected by the compiler, and in aligning objects in the diagram. You can use the commands of the View menu for zooming the diagram in or out. The FBD editor fully supports drag and drop for moving or copying objects. To move objects, select them, and simply drag them to the desired position. To copy objects, just press the Control key while dragging. Alternatively, you can use classical copy-cut-paste commands. The FBD editor enables you to insert an object on an existing line, and automatically connect it to the line. This feature is available for all objects having one input pin and one output pin, such as variable boxes, contacts and coils. That completes all the skills needed for programming in function block diagram. Let's do some exercises. In exercise 2A, we'll write a program in function block diagram to control a conveyor. The conveyor system has the following control actuators and sensors. Conveyor 1 stop is a momentary switch, normally open, which stops conveyor 1 when closed. Conveyor 1 start is a momentary switch, normally open, which starts conveyor 1 when closed. Conveyor 1 overload is a normally closed contact, which opens when overload is detected on conveyor 1. Conveyor 1 run, close to run conveyor 1, open to stop. Conveyor 1 safety stop is a normally closed contact, which opens to stop conveyor 1. Make a function block diagram, which controls conveyor 1, according to the following rules. Pressing the momentary start switch starts the conveyor. The conveyor remains running when the switch is released. Pressing the momentary stop switch stops the conveyor. If the overload contact opens, the conveyor stops. If the safety stop opens, the conveyor stops. We'll start by adding a new program. Call it Exercise 2A. Programmed in FBD. Then open it for editing. Next, we'll create all the needed variables. Conveyor 1 stop. Conveyor 1 start. Conveyor 1 overload. Conveyor 1 run. Conveyor 1 safety stop. All are booleans. We need to set an initial condition of true for the overload and safety stop variables, since they are normally closed. This would not be necessary in a real system, because the I/O scan would set these values for us when the program starts. We'll start with a comment, so we know what the program is for. This control can be accomplished with simple Boolean functions, or an AND. First, add a Boolean, or, function. Connect as inputs, conveyor 1 start, and conveyor 1 run, to latch it in for running, after the push button's released. Then add the Boolean, AND, function. Give it 4 inputs. Insert variable blocks for the added pins. Connect the variable blocks to the function. And connect the output of one function to the input of the other. Attach variables conveyor 1 start, conveyor 1 safety stop, and conveyor 1 overload. Then we have to negate the stop input. And conveyor 1 run to the output. That completes our program. The first function block starts and latches the conveyor on. The second function block keeps it running, as long as the stop is off, and the overload and safety stop are on. Let's test our program and see how it works. We'll disable our practice program, since it has errors in it that won't compile. Then compile. Good, no errors. Now simulate. Turn on conveyor 1 start. And it starts. Activate stop. And it stops. Activate safety stop. And it stops. Activate overload. And it stops. Everything is working as expected. A successful project. In Exercise 2B, we'll add a second conveyor, with an identical set of sensors and actuators. Then add logic to control conveyor 2, according to the following rules. Conveyor 1 must be running to operate conveyor 2. Anytime conveyor 1 stops, conveyor 2 should also stop. Pressing the momentary start switch starts the conveyor. The conveyor remains running when the switch is released. Pressing the momentary stop switch stops the conveyor. If the overload contact opens, the conveyor stops. If the safety stop opens, the conveyor stops. Add the variables for conveyor 2. Conveyor 2 stop. Conveyor 2 start. Conveyor 2 overload. Conveyor 2 run. Conveyor 2 safety stop. Then add the diagram for conveyor 2. We'll adjust the conveyor 1 diagram a little, to make space. Now make a copy of it, to save time redrawing it for conveyor 2. Relabel the first block for conveyor 2. Change this one to 5 inputs. Relabel it for conveyor 2. Bring in a variable tag for the added input. Connect it and label it with Conveyor 1 Run, to force it to be on, before running Conveyor 2. Set the initial values for the overload and safety stop. Compile and run in the simulator. Turn on Conveyor 2 Start. The conveyor doesn't start because Conveyor 1 isn't running. So start Conveyor 1. And now start Conveyor 2. It comes on. Check the stop and safety stop switches. And finally, verify that if we turn off Conveyor 1, Conveyor 2 also goes off. And it does. Another successful application. In Exercise 2C, 2 safety warning horns are added, 1 for each conveyor. We'll add logic to our program to sound a warning horn for 5 seconds after pressing the start button, before the conveyor starts. We'll use the pulse timer to sound the horn on the push button, then use the falling edge of the horn signal to start the conveyor. We'll create the variables we need. Conveyor 1 and Conveyor 2 horns. Timers for the 2 horns, with type TP, pulse timer. And 2 variables for the falling edge detection function blocks, with variable type, ftrig. To modify our program to support the warning horns, first we'll make a couple of adjustments, to make space. To operate the horn 1 timer, we'll add a pulse timer. Attach the start and horn output variables. And give it a 5 seconds time. The horn 2 timer is done similarly, except we'll have to use a Boolean block to require that Conveyor 1 is running first. Then add a horn 2 timer block. Add the time. Attach variables. We'll make a couple of adjustments, to make space. To handle the conveyors, we add a falling pulse detection block, to trigger the conveyor to start on the falling edge of the horn. This block replaces the start input on each conveyor. We're ready to compile. No errors, so go to simulation. To test our completed program, we'll turn on the Conveyor 1 start switch. If everything is working, we should see horn 1 come on for 5 seconds, then horn 1 goes off, and Conveyor 1 comes on. That's exactly what happens. Conveyor 2 should operate the same way. And it does. Another successful application. In the Workbench Course 1 training manual, there are 3 more exercises to help you develop proficiency with programming in function block diagram. Exercise 2D implements a simple volume control. Exercise 2E simulates a car park control. And in Exercise 2F, you will develop a basic heating control. We encourage you to complete those exercises before proceeding to the next section of Training Course 1. That completes Course 1, Part 5. Here's a summary of what we've covered so far. Introduction to Workbench and IEC 61131. Basic concepts of Workbench. Getting started programming in Workbench. Programming in ladder diagram. And programming in function block diagram.